We are going to continue with lesson 2.5 on implicit differentiation. This time we're going to find dy dx implicitly for the sine of y equals x. Okay, so let's just start there. Let's find dy dx implicitly for sine of y equals x. So of course we're going to find the derivative, just to remind you guys, with respect to x of sine of y, and the derivative with respect to x of x. Okay, so essentially we're going to take the derivative with respect to y. So remember, the derivative of sine is cosine, but we also need to take the derivative of the inside function, which is just y, with respect to x. So that leaves you with cosine y dy dx. And then the derivative of x with respect to x is just 1. So that means that dy dx is going to be 1 over the cosine of y. So what that means is we're going to, we could rewrite this, right? Instead of 1 over the cosine of y, we could write that as the secant of y. Okay, so those are some different ways that we could write dy dx. And again, usually like we would prefer the secant of y. Okay. So that's the first part. The next thing it asks us to do, it says to find the largest interval of the form that y is between negative a and a, such that y is a differentiable function of x. Well, there are some issues when we have the vertical tangents, right? So here we have some issues. And then it says that it wants us to have like a negative value to a positive value. This looks really nice, doesn't it? From here to here. So we can say we can see from the graph that it's differentiable and from negative pi over 2, because remember we're going from the y's, to pi over 2. Notice I did not include them because it's not differentiable at those points. Okay, so what that means is that, so the largest interval that you could differentiate this on would be from negative pi over 2 to pi over 2. And I'm putting that in terms of y because that's what we differentiate, like that's what our dy dx was in terms of, right? But now I want us to kind of think about this like as a little puzzle. So what that means is that now that this is a continuous interval on which this is differentiable, what that means is that we should be able to write dy dx explicitly as a function of x. Well, how in the heck are we supposed to do that? Well, let's think about that. Let's consider the function, or let's consider, not the function, let's consider the Pythagorean identity. That the sine of y squared plus the cosine of y squared equals 1. And we know that the cosine squared y equals 1 minus sine squared y. So I can take the square root, right? And cosine y could be plus or minus the square root of 1 minus sine squared y. Okay. But we know that on this interval, we're only going on that interval negative pi over 2 to pi over 2. And when you think about the cosine function on that interval from negative pi over 2 to pi over 2, cosine is positive on that interval. if you think about the original cosine graph, not this graph, the original cosine graph, right? It's greater than 0. So what that means is we can say that the cosine of y is going to be the positive square root of 1 minus sine squared of y. Okay? Now bear with me. All right. So now I want you to consider the given function. Our given function was that sine of y equals x, right? That was our given function. And so what this means is that this sine of y, notice this is really saying sine of y squared, right? So that means that the cosine of y can really be written as 1 minus x squared, the square root of 1 minus x squared. So do you see how I can replace this sine of y with this x because of that given function? Because in this problem, that's what x is. In this problem, x is the sine of y. And what that means is that if we wanted to, that means that our dy dx is going to be the reciprocal of this, right? Because secant y is the reciprocal of cosine of y. So our dy dx can really be rewritten as 1 over 1, the square root of 1 minus x squared. So sometimes it might be in our best interest, you know, to try to write it in terms of one variable versus another. And so sometimes we'll have to be a little tricky as far as that goes. And again, these are not things that I think would be intuitive at the start. These are things that we can see that from here we can, you know, use. And again, a lot of times when we're stuck, those Pythagorean identities can kind of help us out a little bit. Let's do another one where we don't necessarily have to be so creative, but we still have to do something, all right? So with implicit differentiation, the form of the derivative can be simplified, like our last example, by clever use of the original equation. Now, by this clever use of original equation, I would like you to think about this as being fun, like a puzzle, okay? It's going to be fun. All right, so we're going to use a similar technique can be used with higher order derivatives that can be obtained implicitly. So we're going to kind of use our other answer to kind of go forward a little bit. The only benefit is that it might give us an expression that's easier to work with, but one of the biggest things is that it can often eliminate variables. All right, so let's find the second derivative implicitly of x squared plus y squared equals 25. And this says in terms of only y, okay? And again, this wants the second derivative. So let's see what we can do. Let's start by taking the first derivative, all right? So we're going to take the derivative of x squared plus y squared. So we're going to differentiate x squared plus y squared with respect to x. That's going to give us 2x plus 2y dy dx. And then if we differentiate 25 with respect to x, that gives me 0. Okay, this isn't bad. All right, so that means that I have 2y dy dx equals negative 2x. And so then dy dx is negative 2x over 2y. So that means that dy dx is negative x over y. Okay, so that's cool. All right, so that's the first derivative. So now the issue is we want the second derivative. So if we want the second derivative, now we need to differentiate this. Okay, so now we're going to differentiate this. So if I differentiate, maybe I should write So I'm going to take that dy dx and the negative x over y, and I'm going to differentiate that with respect to x, okay? So we know that this is the second derivative with respect to x, okay? And we're going to have to use quotient rule here, aren't we? So we're going to take low d high, so the derivative of negative x with respect to x is -1, minus high d low, so that is just going to be dy dx over low squared. Okay, that's not bad. So I get -y plus x dy dx over y squared. So what am I supposed to do here? I'm trying to find the second derivative, but it looks like we're stuck, doesn't it? Wait a minute. Okay, it looks like we're stuck. So we seem stuck, but we are not. Because don't we know that this dy dx is really -x over y? So we can replace that dy dx with -x over y and simplify from there. All right, so essentially we are replacing the dy dx with what we got for our first derivative, which was -x over y. And then I would just a little bit. So I'm going to clean that up by multiplying by y over y. So that gives me -y squared minus x squared over y cubed. And I might factor out a -1 for that, right? So I get negative y squared plus x squared over y cubed, okay? Again, we seem stuck, don't we? Because this is beautiful for our second derivative, except it wants it only in terms of y. Well, I still have this x, what can I do? Oh my goodness, look how exciting this is, you guys. Again, let's think about our original equation. Our original equation said that x squared plus y squared was 25. And look what we have here. We have x squared plus y squared essentially, right? So what this tells me is that if I want my second derivative, then that's going to be -25 over y cubed. So this y squared plus x squared really is the same as that 25 from the original equation. Isn't that fun? So it's like this little puzzle. You if you seem stuck, go back into other parts of the problem and see if you can pull anything from that, okay? All right. Last one in section 2.5, I think. Yes, good. All right. So this one asks us, in the homework, we'll tell you if it must be in terms of x or in terms of y only or something like that. So just make sure you look at the homework and you're paying attention to like what you want to differentiate for, okay? So pay attention to directions. As far as in terms of x or y only, okay? So if your answer doesn't match, then maybe just double check the directions and see if there's something else you can do, okay? All right, example 9. Find the tangent line to the graph of x squared times the quantity x squared plus y squared equals y squared and then we're going to find it at this specific point, root 2 over 2, root 2 over 2. I don't really want to use the product rule here on that piece. I might revise this equation at first, so I might start by distributing the x to the x squared and ending with x to the 4th plus x squared y squared equals y squared. I might do something like that, okay? And then what we can do is we can take the derivative with respect to x of that, because again, the tangent line, we're going to want the slope, blah, 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 okay? So again, I'm going to take the derivative with respect to x of both sides. And let's see what we get. So these match, so I can just write that as 4x cubed. Oops, you can't see. Oh yeah, you can. 4x cubed plus, we're going to have to use the product rule here. So I'm going to use x squared times the derivative of y squared with respect to x. So that means that's going to be 2y dy dx. Now I want to add y squared times the derivative of x squared with respect to x. So that's just 2x dx dx, which is 1. And then over here, we're taking the derivative of y squared with respect to x, though. So that's 2y and then dy dx. Okay. All right. So I guess that's good enough. I can put all of these over to one side, all the terms involving dy dx. So this is a term involving dy dx, as is this. So these terms, I'll clean it up a little bit too. So 2x squared y dy dx minus 2y dy dx can be equal to negative 4x cubed, and then I'm going to turn that into negative 2xy squared. Is that okay? All right. Then I can factor out dy dx, and I have 2x squared y minus 2y. And then I can divide by 2x squared y minus 2y. And that's my dy dx. So negative 4x cubed minus 2xy squared all over 2x squared y minus 2y. Now, do you guys see that we could do something else? Do you guys see that all my terms are divisible by 2? So all 4 of these are divisible by 2. So maybe negative 2x cubed minus xy squared over x squared y minus y. That's acceptable. Oh, you can't see what I'm doing. Sorry. Anyway, that's what I did. I just divided everything by 2. That's acceptable. Again, there are so many acceptable ways. You could factor it if you wanted to too. So you could factor, sorry about that again, so embarrassing. I could factor, I always like my leading coefficients to be positive, so I'm going to factor out a negative x, and then that leaves me with 2x squared plus y squared, and then in the denominator I could factor out a y, and then that leaves me with x squared minus 1. I don't know, that looks a little better. So there's my derivative, there's my dy dx. And so now it's asking us to specifically evaluate this at, no, you can't see that, at root 2 over 2, root 2 over 2. Okay, so now we'll evaluate at the root 2 over 2, root 2 over 2. Okay, again, just from that directive up here. So now let's put our dy dx in there. So our dy dx is going to be negative root 2 over 2 times 2 times root 2 over 2 squared plus root 2 over 2 squared. Let me change that to this here. Over root 2 over 2 times root 2 over 2 squared minus 1. Jeez, it's a lot of root 2 over 2's. All right, and so let's think what we could do to simplify things a little bit. The nice thing about when we factored this is that since those match, we could cancel that out. And then let's think about, so that leaves me with a negative here. Let's think about what we know about this. Root 2 over 2 squared is going to be 2 over, like plain 2 over 4. So that's going to be 1/2. And so anytime we have the root 2 over 2 squared, that's going to be 1/2. All right, so this is going to be 1 plus 1/2, so that's going to be 3 over 2, so that's going to be negative. There's a negative up here, so negative 3 over 2 over 1/2 minus 1 is negative 1/2. So I can see that at that specific point, my dy dx is going to be 3, positive 3. Do you guys agree with that? And so then the last thing, so that's if they wanted the slope. And so the next, the last thing is we're going to write the equation using the point root 2 over 2, root 2 over 2, okay, with that slope. So I like to use that point slope form, y minus root 2 over 2 equals 3 times x minus root 2 over 2. Yeah, we could distribute. So that would be what, 3x minus 3 root 2 over 2. And then I could add root 2 over 2. And that would give me negative 2 root 2 over 2, which the 2's cancel, right? And so then we just end up with y equals 3x minus root 2. And that is your equation of the tangent line. I mean, so that's a fun party trick, right? Okay, so anyway, point is that we can now use, like, this is really what we've been doing all along, right? We've been finding the slope, putting something in for the slope, then using the slope to write equations of the tangent line. We've been doing that. It's just now we can use this strategy of implicit differentiation to help us with functions that we couldn't do that with before, okay? All right, happy differentiating. Have a great day.